and we have to design our structures for this demand. Okay. 2-3 small topics remaining, that those I will talk now, and then we will take up the assignment. Okay, so we talked about deterministic seismic hazard assessment and probabilistic. So using probabilistic seismic hazard assessment, PSHA, at any site, we can get what we call hazard curve. Okay, so hazard curve is the relationship between the probability of occurrence and any spectral ordinate. This spectral ordinate is value of response spectrum curve corresponding to any period. So this can be corresponding to any period. Okay, corresponding to 0 period also you can take it. When it is corresponding to 0 period, it will be EPGA. So for any value of SA corresponding to any period, if we plot it, the curve looks like this. What does that mean? That the lower values of SA have higher probability and higher values of SA have lower probabilities. Okay. This curve is approximately linear in log. Let me check whether it is, equation is given in natural log. Yes, natural log. So if you take okay, so SI means S at any period Ti. So at a given period it is there. So this is approximately linear. So if you know this value at 2 probabilities, at any other point you can calculate. But keep in mind, this is approximate relationship. Actually it changes from site to site. So an approximate relationship given in FEMA 273 is that log of SI is log of SI 10% in 50 years. SI 10 in 50 years means what? dB. Okay. So this is the value of that spectral ordinate at dB plus log SI 2% in 50 years minus log SI 10 in 50 years into 0.606 log of PR minus 3.73. This is empirical relationship. So you can see this is equation of a straight line. SI is anywhere. Okay, and this is, let us say, SI 10 in 50 years. This is SI 2 in 50 years, 2% in 50 years. Anywhere else you can obtain, for any other probability of accidents you can obtain, and probability of accidents is coming through this PR. PR is average return period. And this average return period, PR, is given as 1 over 1 minus e to the power 0.02 natural log 1 minus P E in 50 years. Okay, so this P is 2%, 10%, it will be given in fraction. So 2% will be 0.02, 10% will be 0.1, okay? And then this will be the return period in years. So for example, you can calculate for 2% in 50 years, what return period you are getting, substitute PE equal to 0.02 and calculate what you are getting. Two 475, okay, and for 10% put P is equal to 0.1. 475 years. So this formula will give you PR. That PR, suppose I want you to determine corresponding to 2% in 50 years. Sorry, 5% in 50 years. So dB and MC value is given. As per current code, it is half of 1.5 into Z by 2 is dB and 1.5 Z is MC. And if I ask you to calculate it for, let us say, SA 0.8. So at 0.8 second, you know the value of SA. Okay. You can substitute corresponding to dB and MC here and then calculate PR corresponding to 5% in 50 years. So corresponding to 5% in 50 years, what is the value of PR? Sorry, 975 years. So that 975 years you will substitute here, you will get the value there. So naturally for 5% in 50 years will be somewhere in between 10% for 50 years and 2% for 50 years value. Okay, so this is called hazard curve. Now such curves you have to plot for different values of lambda and SA at different periods. Let us say 0.1 second. Then you can plot it for SA at 0.2 second. You can plot it for SA at 1 second and so on. So what you can do is, for a given value, 2% in 50 years, here you can read. Then for 2% in 50 years, you can read from here. And from 2% in 50 years, corresponding to that, you can read from here. Okay. So from each hazard curve, and each hazard curve is representing a different period. Okay. So SA corresponding to any period we can obtain from here, or for that matter, any spectral ordinate we can take. And If I plot these corresponding to the period, let us say 0.1 second, 0.2 second, 1 second, and so on, so I will get a curve. This is called uniform Hazard spectrum. In short, UHS. What is given in the code is idealized shape of UHS. Now, you can tell me why we are calling it UHS. This is the idealized shape. This is given in the code. So what code gives is idealized. Actual shape is like this. So what is given in the code is representing UHS, uniform hazard spectrum. And why we are calling UHS uniform hazard? Because this corresponds to equal probability of accidents at all periods. So the probability of accidents of this hazard at all periods is uniform. That's why we call it uniform hazard spectrum. And you can see that uniform hazard spectrum is not caused by single earthquake. It is considering the peak value at this period or the value corresponding to given probability, okay, at each period, and that may be caused by different earthquakes. Okay, in some cases it may be if there is the hazard is dominated by one single source, you can get from one earthquake, one source also, but many cases you will get it from different earthquakes. So it is not the shape of response spectrum of a real earthquake. Okay, this is a shape obtained from an envelope of different earthquakes. This we have to keep in mind, and we will use this when we will be selecting ground motions. So while selecting the ground motions, you have to keep in mind that one single ground motion is not going to give you this shape. The shape of the response spectrum of the ground motion will be different than this, because it is not representing one earthquake. It is representing envelope of several earthquakes. Okay. Now let's see what is there in the current code and what the new code has. So first of all, the real hazard curves. So this is hazard curve corresponding to 0.2 second period. Okay, axes are rotated. So here it is, spectral acceleration is here, and probability of accidents in reverse order. So you can see here the probability is lower and here it is increasing. So you can see this is the real shape. It is not exactly straight line, you can see, close to straight line. So what I have given as a straight line is an approximation. So if you do not have the actual shape and you know the value only at dB and MC, then you can use that shape. But you have to keep in mind actual shape is somewhat curved even under log. This is plotted under log. Okay, so in log also it is not exactly straight line, and this has been done for different countries in different cities in US. Los Angeles, San Francisco, Seattle, Salt Lake City, New York City, okay, and so on. So you can see that different cities, these curves are different, and these have been normalized with respect to MC. That means 2% in 50 years, you can see all the values are same. So these have been plotted in such a way that the normalization has been done with respect to MC. So you can draw a line corresponding to 10%, that is dB. So ratio of dB and MC, if you see here, it is changing. It's not constant. In different cities, the ratio of dB and MC is different. Okay. The maximum value of this ratio is 1 over 1.5. But the value ranges somewhere here. This is value of 2. So from 2 to 1.5. So ratio of MCE to DVE will be somewhere between 1.5 to 2. In our code, existing code, we are considering it as 2. In US, ASC 7, they are considering it as 2/3. Okay. Recent code, they have changed it. Now you can get the MC and DV directly also. Okay. So this ratio considered in our code and other codes is different. Actually, it will vary from site to site, place to place. And if you look at the load factor, this is also interesting. Where the 1 point factor is there, in our code, okay, this is AC 7, not our code. You look at AC 7. In AC 7, the coefficient for earthquake in load combination is 1. Okay, but for serviceability load combinations or working stress methods. So in our code, the load factor is given 1.5. And I told you actually it is not load factor. It is a conversion factor from mean of DSHA to 84 percentile of DSHA. Okay. Now why that 1.5 is capped if it is causing so much confusion? The reason is that some of the designs we are still doing using working stress method. And then some checks we also apply at serviceability limit state. Although in case of earthquake, serviceability does not have much meaning because we are designing our structures not to collapse under MC. That is our intention. But we also want that for smaller earthquakes, the structure should remain serviceable. Okay. So in some structures, there are checks at ultimate limit state and serviceability limit state. Especially like you are designing a bridge as per railway code. Then it has earthquake related check at serviceability also, at limit state, ultimate state also. Okay. Then steel code in railway is still working stress. In highways, it has been changed to limit state. Okay. Masonry design is still based on working stress method. Limit state method is still not developed there. So you need limit state, earthquake hazard, earthquake demand for limit state method as well as working stress method. So as the name suggests, working stress method or serviceability limit state corresponds to serviceability earthquake. And serviceability earthquake is Z by 2. Yesterday we discussed. So first we calculate corresponding to serviceability earthquake. And then we multiply it by 1.5 to convert this into limit state combination. In US, it is opposite. They first calculate corresponding to limit state. And then serviceability limit state is 0.7. That is nothing but this divided by 1.5. So ratio between limit state and serviceability state is same. And from where this 1.5 ratio is coming? Ultimate objective is that whether you use you use working stress method or you use limit state method, the strength of the structure should be same. Because earthquake doesn't know by what method you have designed your structure. Earthquake will understand only the yield strength of your structure. So whatever method you design, the yield strength should be more or less same. So it is basically the ratio or the difference in the factors of safety, partial factors of safety, which we are having in limit state and working stress. A simple example you can take. What is the material factor of safety in ultimate limit state for steel structure, structural steel? Any idea? 1.1. Okay, it varies in different actions. It's approximately 1.1. And in case of working stress method, what is the permissible stress? How much is the permissible stress? 0.6 times Fy. Okay, so you are using Fy by 1.1, that is approximately 0.9. So 0.9 times Fy you are using in limited state method, 0.6 times Fy you are using in working stress method. So what is the ratio? 1.5. So that is this ratio. Incidentally, this is by chance that the ratio between the design basis earthquake and the serviceability level earthquake also comes out to be 1.5. Or historically, that's how the DBE has been obtained. Okay, we have defined DBE as 10% in 50 years. We could have defined 8% in 50 years or 11% of 50 years. Why this came? So that the ratio is approximately 1.5. Initially, all the structures were being designed using working stress method. So at that time, they were using serviceability method. Then the limited state method came. Then they had to define another level of earthquake which should be used in limited state method so that there is a parity in the design. So that's how this ratio 1.5 came, and that corresponded to approximately DBE, 10% in 50 years. Now, still there is a problem in our current design method, and that is that we want our structures to remain stable, not collapse under MC. That's our objective, that under MC, under major earthquake, our structure should not collapse. But we never design for MC, we design for DBE. So that's another problem. What happens to that DBE versus MC? You are designing for DBE, and actually your intention is that it should survive MC. So why or how it can survive MC if you have designed it for DBE? And MC is 2 times of DBE. So how it can survive 2 times the earthquake then, or 1.5 in American code, than what you are designing for? What is that factor? How they came with MC? Why MC is 2% in 50 years? Why not 1%? That factor is called overstrength. So if you design let us say you design a beam. Let's take a simple example. You design a beam as per IS 456 using limited state method. Okay, you will get certain capacity, or you can design it for certain capacity and then test it in the lab. Will you get the same capacity? You design using limited state and then test in the lab. What do you expect? Shall it fail at the same strength? Let us say I test 100 beams. Okay, not one. Because in one beam, experimental errors may be there. So if I design 100 beams, okay, what strength you are expecting from those 100 beams? Average strength, let us say. Average of those 100. What should be the strength? Should it be equal to what you have designed? Should it be higher than that? Should it be lower than that? How much higher? Target? Target mean strength. What is target mean strength in case of beam? Target strength is in case of concrete mixed design. And what is the target strength? Okay, so why we target 1.64 sigma plus 1.64 sigma? So we design for 95% confidence strength, which we call characteristic strength. 95% confidence mean not more than 5% samples should have a strength lower than that. Okay, but if you test 100 cubes, what will be the average strength? Plus 1.64 sigma, because that's how you are calculating 95% confidence strength. So one reason of this strength being higher is that you are using characteristic in place of mean strength, you are using characteristic strength. But when you will be testing, the strength will be actually close to mean strength. Most of the beams will have a strength close to, out of 100, okay, 95 will have a strength higher than what you have considered in your design. Okay, so that is one source of this difference in the strength. Any other source? we are using partial factors of safety. Okay, we have used a factor of safety of 1.5 on concrete. In case of beam, concrete does not govern the strength, because usually we will be designing under reinforced, and steel will be governing the strength. Okay, so we have applied a partial factor of safety on steel also, and steel strength is also, actual strength is higher. In steel, when you calculate Fy, it is also not mean strength, it is also characteristic strength. So that will also have a higher strength, plus 1.64 sigma. And then in steel, there is strain hardening. So due to strain hardening, the ultimate strength will be even higher. So the strength which you will get from testing will be much higher. Okay, because of the partial factors of safety and characteristic strength and strain hardening. Actual strength will be somewhere between 1.5 to 2. Incidentally, that is the ratio between MC and dB. Okay, so we are designing for dB, but actually our strength corresponds to MC, the actual strength. This difference in the actual strength and the strength which we have designed for, this is called over strength. We will talk about this more detail when we will talk about structures. But this ratio between MC and dB, dV and SE, this is related with our design procedure. Okay, these have been obtained because our design procedure, and that is same as for other loads. We are not having a different design for earthquake. The design of RCC or steel members is same as we do for gravity, same partial factor of safety we are using, okay, and same definition of characteristic strength we are using. So our definition of strength and method of design remains same for all the loads. So to calibrate that with earthquake, we are using these factors. So factor between limit state and serviceability design is 1.5. Okay, yield capacity to design strength, that is between 1.5 and 2, and that's how the factor for this, or the ratio between MC and dB, has been calibrated. That's how MC has been defined. So it's not that 2% in 50 years came from, it came some sacrosanct value from somewhere, from God, that you design for 2% in 50 years. That's how historically we have been designing. So we are matching. So historical practice has a very big role in our codes. How we were designing, okay, how those structures performed, whether that performance was acceptable or not. If not, let us increase it. Okay, so that's how these probability of accidents and design procedures have been calibrated. Okay, so this ratio here is also 1.5 in our code. Okay, it is now, this is the revised code which is in wide circulation. Here also you will see that the factor of earthquake load has been made 1 in contrast with the current code. In current code, it is 1.5 dead load plus 1.5 earthquake load. Here it is 1.5 dead load plus 1 times earthquake load. And in the serviceability condition, this is dead load plus EES, EED and EES. So serviceability earthquake, here it is design level earthquake. And these have been differentiated by return period. So rather than using an A factor, this is simply being taken for a return period. Serviceability earthquake is directly considered here. So these return periods for serviceability check and strength check vary for different structures. Ordinary structures, normal structures, strength design, that means limit state design, will be done for 475 years. That is DBE. And serviceability will be done for 73 years, 50% probability in 50 years. Important structures, okay, it is 975 years and 225 years. And in case of critical and lifeline structures like hospitals, it will be designed for MCE. Okay, so this change in the design philosophy is there, which is going to occur, I hope, within your degree program itself, within these 2 years. So at the moment, we are designing all the structures for 475 years. Now onwards, when this code comes, this code becomes effective. Code is already public. So we will be using for some structures 2475 years, and you have to understand which structure, what return period is to be used. Okay, so there will be different return period for limit state design, different return period for serviceability design. Okay, not the factor. And if you look at these values, this is the new zoning of the country. Currently, how many zones are there? 4. Now there will be 5 zones are proposed, starting from zone 2, but a zone 6 has also been introduced here. So this is the zone 6, central Himalayan region and Bhuj, Kutch area of Gujarat. This is in zone 6. So whole of the central Himalayan region right up to northeast. Most of this was zone 5 earlier. No, zone 4 and zone 5, there were some northeast, and this was in zone 5, and here there were some pockets of zone 5. Now whole of this region has been defined in zone 6. And between Delhi and Himalayas, a new zone here, where we are located, Roorkee, zone 5 has come in the foothills. So a new zone has come here. So there, zone 5, zone 6, Delhi is still in zone 4. Okay, and the Z value, what is Z? EPGA. Current code, EPGA for DSHA. Here this EPGA has been obtained from PSHA. So Z obtained from PSHA corresponding to different return periods is given here. So corresponding to 2475 years and 475 years. You look at the ratio, what do you observe? No, you are missing something. Look more carefully. So it is not constant. The ratio between DB and MC is not constant. As I told you, the ratio between DB and MC changes. Okay, so up to in the lower seismicity zone, okay, the ratio is 2. In higher seismicity zone, zone 4, 5, this is 1.5. And look at the value. What is the maximum value now of EPGA? MC 0.75. And what is the value currently? Always multiply by 1.5, I told you. Okay, so from 0.54, we are going to 0.75. In Roorkee, how much is the change? In Roorkee, what is the change in PGA as compared to the existing code and the proposed code? Currently, Roorkee is in which zone? Roorkee is in zone 5. 4. In zone 4, what is the value of EPGA? .36, and proposed value is 0.45 for Roorkee. In which zone Roorkee is? Just now I told you. So increase is absolutely doesn't make sense. You give me the ratio. How many, what percentage it has been increased? How many times it has been increased? Increase of 0.2 in 0.75 will mean different. Increase of 0.2 in 0.1 will mean something different.
6.67.
Okay, so 67% increase has been done. So the design forces will increase by 67% or even more. Okay, look at the spectral shape. So we talked about the site classification A, B and C. So actually it is NEHRP classification which is given ASC 7, 2016 and now 2023 is also there. So the sites are classified as A, B, C, D and E and based on the shear wave velocity. ASC American code uses feet per second. So roughly 3 times you can take. So they have 2 types of rock, rock A and rock B. So rock B starts from 2500, which corresponds to roughly 800 meter per second. So 800 meter per second above is rock, and they have more than 1600 meter per second as hard rock. So they have hard rock in some regions, they have rock. And then this C is 360 or 400, okay, to 800, okay, and then 200 and then less than that. So this A, B, C, D, E are classified, and similar classification is there in Eurocode. Only thing is that in Eurocode there is only one type of rock, and everything beyond 800 they define as rock. There is no hard rock or soft rock, there is only rock. So site class A of Eurocode is equivalent to A and B together of American code. They are not distinguishing between hard rock, other are similar. 360, okay, 180, we talked about 200, okay, and less than 180. So the classification is similar, used world over. Actually it was given by NEHRP, so it is also known as NEHRP classification. And then our code, okay, the revised code which is coming, that is giving the classification similar, okay, 760, 360 and 80. So similar classification is used by our code also. Currently, what is the site classification given in our code? Anybody? And on what basis? There is no talk of shear wave velocity. It is based on n value. Okay, and it is classification is not very clear that what is hard, what is medium, what is soft. Okay, very qualitative type of classification is given. This is now more reasonable. Okay, and shear wave velocity. Do you know any test by which we obtain shear wave velocity? Geotech people at least should be able to tell. Anybody from Geotech? Achha, you are also from Geotech. Anybody else? Have you studied any course on soil exploration? You must have seen they are doing in our, what is that test called? So the more reliable test, the most reliable test is what we call cross borehole test. Okay, cross borehole test, we make 2 boreholes into the soil, we put one transducer here, another receiver here, and we transmit shear waves from here and receive here, and then we can get the velocity. So we get the velocity profile along the depth. Okay, that is quite costly. So a relatively cheaper version but not that accurate is MASW. Okay, so what you have seen there is MASW. Google and learn about these tests. At least, I mean, this much all of structural engineers should know, that which test you have to order to classify your site. So you may not learn how that test is done, but as I said, that this test is costly and MSW is not very reliable. And the most commonly used test in industry is SPT, N value. So almost all the cases, N values will be available to you, and this will be obtained, from N value you can calculate equivalent shear wave velocity. Empirical formula is available, okay, in our revised code. You can calculate shear wave velocity and then you can calculate the average shear wave velocity like this. Okay, then the code also gives the depth for which we have to consider the average shear wave velocity, not 30 meters, but what depth we have to consider. So in different cases, so that is also given. Now, once you know the different sites, you have to obtain the response spectrum for that site class. So the ratio of the response spectrum at soil site, that is BCD in our case, and CDE in case of ASC7. Okay, that can be obtained by using a multiplication factor. This multiplication factor also depends on the range of the period in which we are considering. So let us say this is the response spectrum at rock. We call it rock outcrop, where rock is at the surface. If you measure that, then let us say this is the response spectrum. Okay, some value of Z it will have, and then you can plot the shape. That shape is given in all the codes. Now, at the soil, it gets amplified. This amplification here is different than this amplification. This amplification is called FA and this is called FV. So this is site factor in acceleration control range and site factor in velocity control range. So if you know the site factor, original curve at the rock, all the codes provide the response spectrum, the reference response spectrum at rock outcrop. Okay, and then we have to obtain at the site, depending on what type of soil stratum is there. So for that we need these two factors, FA and FV. So this constant portion, this will be multiplied by FA, and this portion, constant velocity range and the displacement range, both will be multiplied by FV. So this amplification in short period and long period is not same. Okay, up till this point it is called short period range. Beyond this point it is called long period range, or acceleration control range and velocity control range, as we discussed earlier. So in short period and long period, these factors, amplification factors, are different due to soil. What does ASC7 give? It gives table for FA and FB. Actually, these tables are available only up to 2016. In 2023, they have a portal. You give your site class there, it will give you the spectrum automatically for that site class. Okay, so they have conducted probabilistic seismic hazard assessment of the whole country. Okay, and any longitude and latitude, any point within the country you can give to that software. From that software is available on USGS website, but it is for US, of course. It is not for other countries. In our case, such software is not available, but the zonation map is there. So our zonation map will be available on website. You give your longitude and latitude, it will give you the zone. Okay. So you look here, FA. Okay. So this is FA, and they use SS and S1. What is this SS and S1? SS is, they don't use the value of Z, rather they use two ordinates. So this value, which is corresponding to 0.2 second, this they are calling SS, and corresponding to 1 second they are calling S1. So in American code, if you look at their zonation map, they do not have a zonation map, they have contour maps. So contour maps for SS and S1 are given, and once you know the value in this range and this range, you can plot the full response spectrum. You need only one more point here from where this displacement control range starts. So they provide contours. If you look at ASC 7 2016, they provide contours for SS, they provide contours for S1, but with different return periods, and TL for the whole country. So these three parameters are required to define this response spectrum fully. What approach our code is having? It is giving you the shape and just the value at 0 period. So you multiply that shape by 0 period, you will get it. Okay, but you will get, in both the codes, you will get response spectrum at rock outcrop. You have to convert that into response spectrum at soil site. And for that, you need to multiply by FA and FV, and FA and FV are given there in these tables. So please look at this table at SS. Look at it carefully. What do you see? What is your observation? What is the maximum value of SS? 2.4. So acceleration in soil site can be up to 2.4 times that on rock. Okay. Any other thing you notice here? What is happening when you go towards right? Here it is 1. Okay. So it is reducing with increasing intensity of earthquake. SS is increasing means what? The Z or PGA is increasing. Okay. So at higher PGA, you can think it like zone 6, 5, 4 and so on. So as you go towards higher zone, this amplification reduces and it becomes almost 1 in higher zones. Why? So there is amplification due to soil when the amplitude is low. But there is no amplification when the amplitude of ground motion is higher. Why? We discussed the phenomena of soil amplification. Using your understanding of soil amplification, can you explain why there is no amplification in case of higher intensity? Let's look at FV also, that is in the long period range. Sorry? I couldn't get your question. Can you repeat?
So you said that at higher amplification we don't have that amplification we observe in soil, retracing. This is because of the time period.
Period of the soil column. Okay. So because it is a general table. Okay. So this does not take into account the specific characteristics of a site. What is the period of the site? So it is giving you an average value on all the sites. Okay. Actually, if you do site specific study, then the period of the site will also come, where this peak is occurring. So that will occur corresponding to a period, and at the other periods it will be lower. Okay. So period will come into picture if you do a site specific analysis, but so far none of these codes take into account the period of the site. Okay. If you want to take into account the period of the site also, you have to perform a site specific ground response study. Okay. What is meant by ground response study? You will give the acceleration at the rock and then it will travel through the soil and you will get at the top. So you can perform different types of analysis. They call it 1D wave propagation analysis, you can do finite element analysis. So by some analysis where you will model the soil, you will apply the ground motion at the base of it, and you will get the ground motion at the top. And then response spectrum in the rock will be different, response spectrum at the surface will be different, and automatically you will get peak corresponding to the period of the soil. So you can do that. But codes cannot provide result, because then there will be infinite number of factors. Every soil, every site will have different peaks, okay, different periods. So it gives average value. What you see here, how much is the increase in long period? Up to 4.2 times. Like what happened in Mexico City, okay? But this also, you can see that it is reducing with intensity of ground motion. So two things you observe. In long period, the amplification is higher as compared to short period. You agree? For a given class, the FV is higher than FA, okay? Secondly, both FA and FV decrease with increased intensity of ground shaking. And FA approaches 1 in higher zones, higher intensity. Why it is reducing with intensity? I told you that soil has two characteristics. It is causing dissipation of energy, damping. Okay, how much damping the soil will cause will depend upon how bigger the hysteresis loop is, or how much nonlinearity or inelastic deformation in the soil is occurring. Higher intensity means higher nonlinearity in the soil, more energy dissipation. Okay, and then due to the reduction in the velocity, there is amplification. So both amplification and attenuation, dissipation, occur within soil. Okay, in case of low amplitude motion, amplification will be more, much more than attenuation. In case of higher amplitude motion, higher intensity motion, the dissipation will overcome the amplification. So you don't see any amplification here. Here you see amplification, and amplification in long period is more, because generally the site period will lie in, when it is soft soil, if it is not rock, the site period will be in the long period range, okay, in the velocity control range. So corresponding to that, the amplification will be more. Okay. Now let us compare this with our code. So our code gives the shape of response spectra like this for site class A and B, C and D. Okay. So this is 2.5. So in our code, in short period, there is no increase. It remains 2.5, 2.5, 2.5. Okay, from 0.1 second to 0.8 second. Okay, so that is our short period range. In long period range, here you see, this is the long period range. Here it is 1 by t, here it is 1.5 t, and here it is 2 by t. So amplification factor for site class C is 1.5, and for site class D it is 2. But it is only in long period range. In short period range, there is no amplification. So if I compare the response spectrum of our code as compared to American code, come on. So American code has both FA and FB, and what is written in white, drawn in white, that is on rock, this is on soil. Our code keeps this same and considers it only in long period range. Our code does not consider any amplification in short period range. And the logic for that, you have seen that in case of higher intensity, in short period range, FA comes out to be 1. although it is not fully correct. Okay, in zone 2, where intensity is lower, so wherever intensity is lower, there you be careful, our code is not correct. Okay, in lower intensity, lower zones, for example, zone 2, if you have a soft soil in zone 2, okay, the response spectrum can be higher than rock in zone 4. Okay, so here you understand the importance of soil. Other aspects of the soil, bearing capacity and solid structure interactions are there, that's different. The ground motion itself due to soil in zone 2 can be higher than that in zone 4 in certain type of soils, not in all types of soils, in certain types of soil. So this you have to keep in mind. Yes.
Instead of ignoring that part, they could have simply considered that for short.
Yeah, they could have done many things, but they have done it like this. It's not that they are not knowing that SC7 is doing this. They know. Still, this is what they have decided. The committee has decided. Okay. And their argument is that the period elongates in case of soil, and site period is not in this range, site period is usually in this range. So we don't see, if you see the real response spectrum, the real response spectrum in case of hard rock will be something like this, and in case of soil, it may be like this. So this corresponds to this period. So usually here you will not get amplification, usually, but that's not true in all the cases. So American code takes into account all the possibilities. Our code is based on a general understanding. Okay. So this you should keep in mind. That's all about hazard. And when we meet on Monday, we will start talking about nonlinearity in structures. Any question here? And now you can complete your assignment number 1. Tutorial 1.